now we will see the basic factor of Bode plot of a basic factor. Pole on the real axis, that is represented by 1 divided by 1 plus j omega t. The log magnitude of this factor is 20 log 1 divided by 1 plus j omega t is equal to 20 log 1 divided by square root of 1 plus omega square t square, that is equal to 20 log 1 plus omega square t square raised to minus half. This minus half, if you are taking this side, it will become minus 10 log 1 plus omega square t square. Now for low frequencies, when omega is very much less than 1 by t, omega is very much less than 1 by t, omega is very much less than 1 by t, the log magnitude may be expressed as 20 log magnitude of 1 divided by 1 plus j omega t is equal to is equal to minus 10 log 1 is equal to 0 dB. The log magnitude curve at low frequencies is the constant 0 dB line. For high frequencies, when omega is very much greater than 1 by t, the log magnitude is approximated as, when omega is very much less than 1 by t, what you can see that this term you can make it to 0, that means it will become log 10 minus 10 log 1. When omega very much greater than 1 by t, then 20 log 1 divided by 1 plus j omega t is equal to minus 10. This term is very high, so this you can eliminate. So you will get it as minus 20 log minus 10 log omega square t square. This square term 2, you can take it to this side, it become minus 20 log omega t, that is equal to 20 log omega minus 20 log omega minus 20 log t. This is an approximate expression for the high frequency range. For log frequency it is 0. This is also approximate, this is also an approximate. But here we need to understand here like using the asymptote, we will draw the approximate Bode plot. After that we will see the error, then you are adjusting, or we are finding the exact plot using that error. Now at omega is equal to 1 by t, the log at omega is equal to 1 by t. The log magnitude equals to 0 dB. At omega is equal to 10 by t, the log magnitude is minus 20 dB. So at omega is equal to 1 by t, at omega is equal to 1 by t, the log magnitude equals to 0 dB. But when you are observing it, you can see that here minus 10 log 1 plus omega square t square, minus 10 log 1 plus omega square t square, when omega is equal to 1 by t, this is equal to minus 10 log, you are substituting 1 plus omega is 1 by t, so it will become 1 only. So you are getting it as minus 10 log 2. So it is not equal to 0. But we assumed, that is why there are some error, we assumed that as Here it is 0 dB are taken, and when omega is equal to 10 by t, the log magnitude is minus 20 dB. Thus the log magnitude decreases by 20 dB for every decade. This is all approximate. Okay, when you are substituting omega is equal to 10t in this, omega is equal to 10, yeah, omega is equal to 10 by t. So here 10 by t. So when this will approximate minus 10 log, you will get around 10. Okay. Yes. 10 by t. Yeah, if the frequency is high, that time you can substitute minus 20 log. Yeah, 10 by t into t. Tt will be cancelled, so you will get it as minus 20 log 10. Minus 20 log 10 is equal to minus 20 dB. So it is equal to minus 20 dB. Thus, as you can see that, thus the log magnitude decreases by 20 dB for every decade of omega. Thus, for omega greater than 1 by t, the log magnitude curve is a straight line with a slope of minus 20 dB per decade. So here we took some approximation and we assume that it is 0, but actually it is not 0. Through the above two straight line approximation hold good for omega with very much less than 1 by t. When omega is very much less than 1 by t, it is 0. That definitely you can say. And when omega is very much greater than 1 by t, respectively, with some loss of accuracy, this would be extended for frequencies with a loss of accuracy, the above. That means when omega is very much less than omega is very much less than 1 by t, it is having 0 dB, and omega is very much greater than 1 by t, it is having a slope of minus 20 dB. Now what we can say that this with some loss of accuracy, this could be extended for frequencies omega less than or equal to 1 by t and omega greater than or equal to 1 by t. Therefore, the log magnitude versus low frequency curve of 1 divided by 1 plus j omega t can be approximated by two straight line asymptotes, one a straight line at omega dB for the frequency range omega between 0 and 1 by t, and other a straight line with a slope of minus 20 dB decade for the frequency range 1 by t omega between 1 by t greater than 1 by t and less than infinity. So that is represented here. As you can see that till 1 by t it is 0. After that there is another asymptote that is having a slope of minus 20 dB per decade. So some loss of accuracy we are approximating near to this point. We are assuming that it is a straight line till 1 by t, and after 1 by t actually this will be 0 for omega is very much less than 1 by t, and for omega very much greater than 1 by t, that time the slope is minus 20 dB, but this condition is extended to omega just less than or omega less than or equal to, this is extended to this omega less than or equal to 1 by t and omega greater than or equal to 1 by t. That means here it is okay, this side also okay, but we are extending that same thing to here as well as from here to here as a straight line. Okay, so the frequency, again there is one important thing is that the frequency omega is over 1 by t at which the two asymptotes meet is called the corner frequency or the break frequency. So here at which the two asymptotes, this is not actual, so this asymptote as well as this two asymptote meet at omega c is 1 by t, and this point is known as corner frequency or break frequency. This omega is 1 by t, that is known as corner frequency or break frequency. Now the corner frequency divides the frequency response curve into two regions, a curve for the low frequency region and curve for the high frequency region. The corner frequency is very important in sketching logarithmic frequency response curves. That is the magnitude of border plot. The corner frequency is very important. So we will study when we are doing the problem. We will come to understand that. Now the log magnitude plot of 1 divided by 1 plus j omega t. Log magnitude plot discussed above is an asymptotic approximation of the actual, but already I told that in the diagram also I told that we are assuming that here it is straight line, but actually it is not. Now the actual plot can be obtained from it by applying the correction for the error introduced by asymptotic approximation. So what you need to do is you should understand this. Then once you understand that, the same thing you directly apply. Okay, everywhere, every time you need not to calculate these values, but for one time you need to calculate. After that, the same knowledge can be applied to everywhere. Now the error in log magnitude curve of 1 divided by, so what you are doing, the actual plot can be obtained from it by applying correction for the error introduced by asymptotic approximations. So error in log magnitude curve 1 divided by 1 plus j omega t for omega greater than 0 and less than or equal to 1 by t. That means almost near to this 1 by t is given by minus 10 log 1 plus omega square plus t square plus 10 log 1. In this example, we assume it as 0. Here there is a 10 log 1 that is considered as an error, 10 log 1. So therefore the error at corner frequency omega is to 1 by t is minus 10 log 1 plus 1 plus log 1. It is minus 3.01 dB, or approximately it equals to minus 3 dB. So error at the corner frequency omega can be calculated as minus 10 log 1 plus 1 plus log 1. It is equal to, we assume that it is 0, but it is minus 3.13 dB. Now the error at half of the corner frequency, that is at omega is equal to 1 by 2t, half of the corner frequency, okay, is minus 10 log 1 plus omega is equal to 1 by 2t, so 1 by 2 all square, that is 1 by 4 plus log 1, it is equal to minus 0.97 dB, so approximately equal to minus 1 dB. So around, as you can see here, the error is minus 3 dB, and if you are going to half of this corner frequency, then you can see that it is around minus 1 dB. Now for other region, this region, what is the error? Now we found the error from here to here. Now for omega greater than or equal to 1 by t and less than infinity, error in magnitude is given by minus 10 log 1 plus omega square plus t square plus 20 log omega t, minus 20 log omega t plus 20 log omega t. So yeah, so therefore the error at the corner frequency omega is equal to 1 by t square is equal to minus 10 log 1 plus 1 plus 20 log 1. This is equal to 0. This one again it will equal to minus 3.03 dB is equal to minus 3 dB. Again at the corner frequency we are getting it as 3 dB. Both left hands when you are calculating error to this as well as error to this at this point is same, that is minus 3 dB. Now the error at double of the corner frequency, that is equal to omega is equal to 2t. Omega is equal to 2 by t. Now before we calculated 1 by 2t, now omega is equal to 1 by t into 2, that means 2 by t around the to the right of this. Double means the error at double of the corner frequency, error of the double of the corner frequency. Then you can see that minus 10 log 1 plus 4 plus 20 log 2, so it is equal to minus 0.97 dB is equal to minus 1 dB. So I think that you got the values. Just understand this. The error equation, you just observe it. We are not going to detail how it is, how we got. This is the error equations. Now this is your initially we drawn the using the asymptote, we plot the approximate Bode plot, and after that we calculated the error. At corner frequency there is minus 3 dB, so you have to get minus 3 dB point at this point. Then error at half of the corner frequency, that means around here, it is equal to minus 1 dB, minus 1 you have to come down. Then error at the double of the corner frequency, around double of the corner frequency, somewhere here also you are getting minus 1 dB. So you have to mark 1 point here, 1 point here, and another point here. Then you have to plot the actual exact plot. Similarly, you can calculate for the error at the error at 1 decade below or above the corner frequency is, again if you are substituting omega is equal to 10 by t or omega is equal to here instead of 1 by 2 0.1 t, then you are calculating it, that means decade, you are getting it as, here it is minus 0.04. Now the varying the time constant shift the corner frequency to the left or right, but the shape of the log magnitude and phase angle curves remains the same. Maybe the corner angle, after the adjustment, the corner frequency it may shift. Yeah, the transfer function 1 divided by 1 plus j omega t has the characteristics of a low pass filter. Now the phase angle pi of the factor 1 divided by 1 plus j omega t is pi is equal to minus tan inverse of omega t. At the corner frequency, when omega is equal to 1 by t, you are getting minus tan inverse of t by t, so it is minus 45 degree. At 0 frequency, pi is equal to 0 degree, and at infinite frequency, okay, at the 0 frequency and omega is equal to 0 as well as omega is equal to infinite frequency, pi is equal to minus 90 degree. At half of the corner frequency, omega is equal to 1 by 2t. In that case, you are getting minus 26.6 degree. At 1 by 10th of the corner frequency, this is octave, this is decade less. Omega is equal to 1 by 10t. So pi is equal to minus tan inverse of t divided by 10t, that is equal to minus 5.7 degree. At the double of the corner frequency, that is again octave, to the right side, that is omega is equal to 2 by t, pi is equal to again, you are getting minus 63.4 degree. At 10 times to the corner frequency, that is omega is equal to 10 by t, pi is equal to minus tan inverse of 10t by t, that is minus 84.3 degree. Again, pi is nothing but, this is your expressions, 1 divided by 1 plus j omega t. Pi can be calculated by, because it is a term is in denominator, so minus tan inverse of the imaginary terms omega t divide the real term, that is 1, so it will become minus tan inverse of omega t. So we got all the terms. I already explained the magnitude plot, and this side it is having a 20 dB decade of slope for the asymptote. Then after that, here it is 0 till omega c. Exact plot, consider the errors, you will get the exact plot. So this is common for this type of expression. This is common, and you can using these values, you can draw the approximate value, and at the phase angle you can draw with this side is log omega and pi. Now when at the corner frequency, pi is equal to minus 45 degree. This is the corner frequency. At corner frequency it is minus 45 degree, and for 1 by 2t around here it is minus 26.6, minus 26.6, this is it is minus 26.6, and at 1 by 10t, one decade around here it is minus 5.7 degree, and double the corner frequency somewhere from the double the corner frequency around somewhere here, from here it is minus 63.4, and 10 times to the corner frequency, that means one decade coming to that time it is minus 81.3 degree, and you know that at 0 frequency pi is 0, and at infinite frequency pi is minus 90 degree. So it is very clear and you can understand this. Now if a transfer function consisting of similar terms, the structure is this should be assembled in the main Bode plot. This is one part of that, so that later we will see how it can be. Now multiple poles on the real axis, that is 1 divided by 1 plus j omega t n. Here what you can see that whatever you calculate here, everywhere there should be a multiplications of n. That's only. Okay, so the log term is minus 10n log 1 plus omega square t square. Here previous case it is minus 10 log. Here there is a multiplying term of power of term n, so that will be in log form, it will come as a multiplying term. Okay, so at omega less than t it is equal to 0 dB. Then at omega very much greater than t, it is 20, before it was minus 20 1 by 1 plus j omega t is minus 20 log omega t, but here it is minus 20 n log omega t. Now the plot, directly you can go to the plot till 0 to omega c 1 by t it is 0, and from corner frequency to greater frequency, this is 10 by t is 1 decade. The slope is minus 20 into n dB per decade. So n, there is a multiplications and approximations. Here at a corner frequency the error is minus 3 into n dB. So minus 3 into 10, that much less. Then yes, here the previous case we'll calculate, this is become 3n. The error of half of the corner frequency, there it is minus n in, minus 1 into dB, that become minus n into dB. At the double of the corner frequency it become minus n into dB. At the decade, 1 decade above and below, it is minus 0.04 into n into dB, like that. Everywhere you have to multiply by n. So the thing is like this with the exact plot. Here it is minus 3 into n dB. Similar the plot also. Everywhere you have to multiply with n. That's only. The shape, everything is same. Okay. Now 0 on the real axis. This is pole on the real axis. 0 on the real axis. Pole on the real axis, the term is 1 divided by 1 plus j omega t. Here it is not 1 by, just 1 plus j omega t. It is exactly reciprocal of 1 by j omega t. So the plot also exactly reciprocal of this one. Exactly reciprocal of this one. You can see here. Yeah. Till corner frequency it is 0. After corner frequency it is, slope is instead of minus 20 dB here plus 20 dB per decade. And the angle starting from 0 at corner frequency, before it was minus 45, here it is plus 45. And it will extend to 90 degree. Now multiple zeros on the axis, that is 1 plus j omega t raised to n. Then the same type of graph, but everywhere you should multiply by n. Yeah. So here plus 20n, here minus 20n. The slope is plus 20n dB per decade. Yeah. Okay. Here also the 1 divided by 1 plus j omega t, you can see that multiplication by n. The same way here also multiplied by, yeah, here multiplied by n. Angle also multiplied by n at corner frequency plus 45 n degree. And if you are going to infinity, it become plus 90 degree ND. If you are in 0, omega is 0, that time it is 0 degree. So easily you can understand and draw. Now the last one in this is quadratic factors. If a complex conjugate poles, now we will complex conjugate poles we will do. For a complex conjugate zeros, it will be like what explained the previous case, that will be exactly reciprocal. So those who are coming down of 0 line will go to the negative side of the border plot, will go to the positive side, like that. Now we will take a first complex conjugate poles, that is 1 divided by 1 plus 2 xi into j omega by omega n plus j omega by omega n all square. Now the log magnitude of this factor is 20 log of this term is equal to minus 20 log square root of 1 minus omega square by omega n square all raised to square plus 2 xi omega by omega n raised to square. For low frequency, asymptote is thus a horizontal line of 0. Now for low frequencies such that omega is very much less than omega n, the log magnitude curve is omega is very much less than omega n. So it is almost equal to minus 20 log 1. So it is 0 dB. This is not exact, approximate. So the low frequency asymptote is that this is a horizontal line at 0 dB for high frequency such that omega is very much greater than omega n. Omega is omega n. The log magnitude curve is when omega is very much greater than omega n. So you can see that this will be, usually xi is very less, so this will be minus 20 log omega square by omega n square. This term is reduced to this, that is equal to minus 40 log omega by omega into dB. So high frequency asymptote is a straight line having a slope of minus 20 dB and till corner frequency, and for low frequency it is 0 dB. So from this you got it. Now the high frequency asymptote intersect the low frequency asymptote at omega is equal to omega n on 0 dB line. This frequency omega n is called the corner frequency. These two asymptotes are independent of the value of xi. These asymptotes are independent of xi because here you can see even if the frequency is very less, there is no xi in this. When the frequency is very high, that time also xi is not there. So these asymptotes are independent of xi. Okay, independent of the value of xi. The corner frequency. These two asymptotes are independent of the value of xi. Now near the corner frequency, omega is omega n, a resonant peak occurs. The damping ratio xi determines the magnitude of this resonant peak. Like this, a resonant peak near the corner frequency, there is a resonant peak and a resonant peak. Now error between the actual magnitude and asymptotic approximation given as follows. For omega between omega greater than 0 and very much less than omega n, the error is actually it is for omega greater than omega and less than, not double here, it is very close to omega n. The error is where you have 2 instead of 2 less than sign, only 1 less than, but here 2 greater than sign should be incorporated, less than sign should be incorporated, but this has a mistake. Near omega n, only 1 sign. Okay, like that. The error is minus 10 log 1 minus omega square divided by omega n square all square plus 4 psi square omega square by omega n square plus 10 log to the 1 is equal to 0. Yeah. For omega n less than omega, the error is minus 10 1 minus omega square by omega n square raised to square plus 4 psi square omega square by omega n square plus 40 log omega by omega n is equal to 0. Here it is minus, that you have to put it as a plus. Here it is a minus, yeah, that you have to put it as a plus here. Now from the above expression it is seen that error is a function of xi and the normalized frequency u, for the normalized frequency u, omega by omega r. Normalized frequency you are taking omega by omega r, that is represented as u. Now the error versus omega by omega n curve for the different values of xi are plotted in the figure 7.26. The correct log magnitude curves for various values of xi are shown in figure 7.25. So correct values. So for xi is equal to 0.5, you are getting 0.05 maximum. If xi is increasing, the at the corner frequency, as you can see that, resonant peak occurs at the corner frequency, but the resonant peak decreases as xi increases. You can see that at 1 it is almost the same. Okay, at 1 you are getting almost flat, otherwise it is the z increases, but here it is corner frequency, that is, this will be the corner frequency. This is the corner frequency. At corner frequency, at a 0.05, you are for xi is 0.0, you are getting highest resonance. After that, the resonance is decreasing. For xi is equal to 1, you are getting a flat curve. And here you can see, here it is 0 dB. After the corner frequency, it is equal to minus 40 dB. That is obtained from this approximate expressions. Okay, this approximate expressions. When you are taking this approximate expression, what that is that in previous case also, the here minus 20 log omega for error calculation, for the actual expression we have to add plus 10 log 1. Here it is minus 10 log 1. You have to add in order to error calculations. You can see this is the more common techniques. Minus 10 log 1 plus omega. This is actual expression. From that, in order to error calculations, for low frequency you are getting minus 10 log 1, but here you should add 10 plus 10 log 1 plus 10 log 1, and at high frequency you are getting here as minus 20 log omega t. For error calculation, plus 20 log omega t, you should add with your actual expressions. For your actual expression. So your actual expression is this.